Joan brings a cup of hot tea into a room and places the cup on a table. At time t minutes after Joan places the cup on the table, the temperature theta degrees centigrade of the tea is modelled by the equation theta equals 20 plus a e to the minus kt, where a and k are positive constants. Given that the initial temperature of the tea was 90 degrees centigrade, find the value of a. The tea takes 5 minutes to decrease in temperature from 90 degrees centigrade to 55 degrees centigrade. Show that k equals a fifth log 2, and find the rate at which the temperature of the tea is decreasing at the instant when t is 10. Give your answer in degrees centigrade per minute to 3 decimal places. So I've got the summary of the question here. So find the value of a. Initial temperature is 90, so let's put it in then for part A. So here our initial temperature is 90. Put that in, is equal to 20 plus a. Now initial temperature means t is 0, doesn't it? Because that's when we start. So t is 0. So all of this is 0 and e to the 0 is 1. So it's just one lot of a, which is a. So we can leave that as is. So read from right to left then. A equals, move the 20, 90 minus 20 is 70. So a is 70. Part B. The tea takes 5 minutes to decrease in temperature from 90 to 55. So in 5 minutes it's 55 degrees C, and we need to show k as a fifth log 2. So let's write down the same equation then, but this time put in the different values. It's 55 degrees now. Theta is equal to 20 plus a, which is 70, isn't it? So let's put that in straight away. E to the minus kt. Now t is 5, so it's 5 times k, or k times 5. So I'll write it that way around. kt, t is 5. And we're dealing in minutes, aren't we? So here we can just move the 20 across. So 30. 50 minus 20 is 30, is equal to the 70. It's 55, isn't it? Which is a bit of a mistake there. 55 degrees. So let's put that in. So this is 35. So tiny little error there. Let's just change that quickly. So 55 minus 20 is 35, is equal to 70 e to the minus 5k. Move the 70 from times to divide. 35 over 70 is a half. Tap it in the calculator if you need to. So a half is equal to e to the minus 5k. Now let's undo this exponential power and reduce it to a log. And doing that, all we do is we swing the e down to be the base of the log. So we get log e, or ln of a half, log base e of a half is equal to. And once that's swung down, this thing that's up in the air just jumps down to ground level. So that's undone the exponential there, written it in log form, the equivalent logarithmic form. So here, what can we do now? Move the minus 5 over here from times to divide. So we get minus, put the minus there, minus 1 over 5 ln 2, ln half rather, is equal to k. So that tells us, reading from right to left, k is equal to a fifth ln of 2. Now the minus is minus one lot of something, isn't it? And I can move that from here up to a power. So it's the half is still there. Sorry. And then this minus 1 here, I'm going to move up to there. So the minus was there, here, and using properties of logs, if I did the reverse, this would come down to get the line that we had just here. So half to the minus 1 is 1 over a half, and 1 over a half is 2, so it's a fifth log 2. So there we are, there's k. So we've done that. Find the rate at which the temperature is decreasing when t is 10. So we need our equation then for part C. So let's give ourselves a bit of room then, and turn our attention to part C now. Theta is equal to 20 plus a, which was 70, e to the minus k, which was a fifth log 2, times t. Okay, so that's log 2 times t, a fifth, log 2 times t. Now, we need d theta dt, don't we? Because we need the rate of decrease, and the rate of increase is d theta dt. Constant differentiates to 0. E to the something differentiates to e to the something. 70 lots of e to the something. It's a function of a function. times t multiplied by the something differentiated. Differentiate this with respect to t, you just get the number here, because the t differentiates to 1, and there's a fifth log 2 of them. Now that's d theta dt, so let's tidy that up. The minus can come to the front. 70 over 5 is 14 ln 2 e to the minus t over 5, isn't it? The t can come to be with the fifth, ln 2. So I'm just going to squeeze that in here, ln 2, if you can read it. So t equals 10. That gives d theta dt then, the rate of increase in temperature, when t is 10, is minus 14 times ln 2. And put 10 in here, minus it's e to the minus 2 ln 2, which equals minus 14 ln 2 e. I'm going to move this minus 2 up to be here, ln 2 to the power minus 2. So that's equal to then minus 14 ln 2. The e to the log cancels each other out. We get 2 to the minus 2 basically, which can come down to ground level now. That's a quarter. So that's equal to minus 14 over 4, or minus 7 over 2 ln 2. Now the answer we need to give to 3 decimal places, so let's just do that then. So we got minus 14 over 2, which is minus 14 over, what have we got here? What did I do? This was a quarter. 14 over 4 that should be, shouldn't it? So let's just correct that, which is 7 over 2. Minus 7 over 2 log 2. So it's minus 7 divided by 2, because I've just simplified that fraction, and then times that by ln 2 equals minus 2.426 to 3 dp. 2.426, and that was to 3 decimal places. So that was the rate of increase when t is 10, so rate of decrease then. So the rate of decrease is just going to flip the sign of that. It's equal to 2.426 degrees centigrade per minute. And that was to 3 decimal places.